Okay, hello everybody. We're going to take a quick look at the homework for section 8.2. I've got two problems picked out, so I think we'll just go ahead and jump right in here. First problem I want to look at is number 3. Okay, and this one is again one of these problems in the beginning where it goes over sort of a step-by-step. So these are hypothesis tests that compare two population proportions. And so those are P1 and P2. We have to determine a null and alternative hypothesis. The alternative hypothesis is one of these. P1 is greater than P2, less than or not equal. Just pick one of them. Null hypothesis is always P1 equals P2. The alternative hypothesis always points to the tail used, so greater than is for right tail tests, less than for your left tail tests, and not equal, that's less than or greater for a two-tailed test. Okay, so it says from a first categorical sample of size 871, 496 successes were observed. Okay, so I think I'll go ahead and just do sample 1 here. Okay, so N1 is, what does it say, 871. Okay, X1 is the 496. Okay, those are the successes. All right, and then I'll be dividing somehow like that. And then we'll do sample 2. And then we'll do sample 2. Where N2 it says is 861 with 548 successes. Okay, so then it says test a claim at 1% significance. All right, I'll put that down somewhere here. I'll just put it here for the moment. Alpha is 0.01. That the samples were drawn from populations with unequal population proportions. Okay, so that's an alternative hypothesis. So if you want, you can write H1. It says the population proportions are unequal, so P1 is not P2. The null hypothesis is always the same. It's P1 equals P2. So these are clearly contradicting one another. We'll either support the alternative or we won't based on our decision about the null hypothesis. Okay, so the null hypothesis, I can go ahead and put it in here. Once again, you're going to use the P1 and the P2 on the palette here. So you can just say P1 and then equals P2 for that null hypothesis. And on this one, the alternative hypothesis, this one's a two-tailed test here, so we'll pick that. Maybe I'll remind myself here, two-tailed test. Okay, and so pick that. Okay, so we're good to go, and I'll go ahead and check that everything's good. So then it says, for the criteria for approximate normality, our preference would be to check the left and right tail lengths in P and in Q for the binomial distributions of each variable. Unfortunately, we don't know the population proportions, so we're forced to estimate the tail lengths using the number of successes and number of failures, which are in P hat and in Q hat for each sample. These must be at least 10. So let's go ahead. I've got the successes for the fails in each sample. This is always n minus x. So you're going to go 871 minus 496. Make a little space for that. All right, 871 minus 496 is 375. And yes, that's greater than or equal to 10. Okay, so we've got both the successes greater than or equal to 10 and the fails greater than or equal to 10 in the first sample. In the second sample, there are 548 successes, obviously greater than or equal to 10. And then for the fails, that's n minus x, 861, minus 548. So that's equal to 313, and once again greater than or equal to 10. So we have a check on all the criteria satisfied. So here we're going to put these in. So for the first sample, successes 496. The failures were 375. All right, so the successes on the second sample, 548. The fails were 313. And all of these are greater than or equal to 10. So yes, the criteria are satisfied here. If I could just get it to recognize that. There we go. And I'm going to go ahead and check my answer here. Should have everything okay so far. We're good. Okay, so now we need to figure out what these sample proportions are. So just to kind of take us back here, p hat 1 is x1 over n1. So that'll be 496 over 871. Move that down a little. Okay, and so we'll do that in a sec. And then our p hat 2 is equal to x2 over n2. Okay, and so that'll be 548 over 861. Okay, so for the first one, 496 divided by 871. Okay, so that with three figures, 0.569. And then our P2 hat, 548 divided by 861. Okay, so that's 0.636. We can put these in real quick. So 0.569 and 0.636. Okay, and those are just fine. Okay, so this, let me see here. We want to go ahead and let's just read what it says here. So my apologies, I've lost my place. Okay, so standard error for the difference between sample proportions requires the unknown population proportions P1 and Q1, which are hypothetically equal. That's the null hypothesis. Our best estimate of this common proportion combines the sample proportions into a single pooled proportion, P bar. So I guess we're going to have to compute that next. And obviously we need Q bar as well. So let's go ahead and I'll make a little space for that here. I think I want it above the hypotheses. So my P bar formula is x1 plus x2 over n1 plus n2. Okay, so the means are the numbers of successes are 496 plus 548. Okay, and that'll be over the two sample sizes added together, 871 plus 861. Okay, and we'll do 3 significant figures on that. This is a little more complicated expression, so I would use the fraction tool on this one and just build it that way. 496 plus the 548, and then over, just pop down to the denominator, 871. Oops, 871 plus 861. I don't want this to come out as a fraction, so if you just put a decimal after any of these values, it'll say, oh, they want it in decimal. So there we go. We'll call that 0.603. And then I'll squeeze in a Q bar here. Q bar is 1 minus P bar. So 1 minus 0.603 is 0.397. Okay, so those are all the main numbers we've got. Let's just put these in real quick here. So for P bar, 0.603, and point Q bar, 0.397. So these should be all fine. I'll go ahead and submit and double check. Yes, everything's good. Okay, and then we go ahead and start evaluating our test statistic here. So let me just put in a formula for that. Okay, so our Z test statistic is P1 hat minus P2 hat, and then minus the difference between the hypothetical proportions, P1 minus P2. The null hypothesis says those are equal right here. So if those two numbers are equal, then the difference will be 0. So I'll just highlight that this is a 0. And then it's over. We'll put in our P bar and our Q bar. This is a mess. Okay, so P bar, Q bar over N1 plus P bar, Q bar over N2. All right, and then we're going to put in numbers. So P hat 1.569 minus P hat 2, which is 0.636. Okay, and then minus the difference between the population proportions, which is hypothetically 0. Okay, and now this mess down below in the denominator here. Okay, so we've got this square root and the P bar, Q bar. So P bar is 0.603, so you're going to go 0.603 times 0.397, okay, over the first denominator, which is 871, that's N1, plus the same numerator, 0.603 times 0.397 over the other sample size, which was 861. And I am going to clean this up a little bit because it's a little hard to read the way I wrote it. So just move that over a bit. Okay, now calculator time. I'll go ahead and clean the screen here on the calculator and start my horrible fraction. Okay, so the numerator 0.569 minus 0.636. Those seem pretty different, by the way. I think that's probably significant. So minus 0, and then, which you don't need to put up there, and then the denominator. So a square root first, and then the first fraction with the numerator 0.603 times 0.397, okay, over first sample size, which is 871, like that. And then right arrow just once, make sure your cursor is still under the square root, okay, and then plus another fraction, same numerator, 0.603 times 0.397. You can't combine these fractions easily. It's probably easiest just to leave them alone and not try and simplify it or anything. It's over 861. Okay, I can't see the whole expression, but I'm pretty sure it's right. You can use the arrow keys to scroll this thing left and right, just to kind of, if you want to just double check everything. But as it stands right now, I'm just going to hit enter. And so there's that's a really big test statistic. So we're going to call that negative 2.85. It wants two places after the decimal. So we'll say approximately 2.85. Negative, right? Yeah. Negative 2.85. Okay, and we can put that in over here. Like that. And we'll check it just to make sure. Hopefully it's right. It is. Okay, so now I guess I could come down. Let's put in the level of significance. We put it here as 0.01. Okay, and now for critical values. We decided this was a two-tailed test, so with a 0.01 alpha. We can go ahead and I'll do a little picture of this. It's a normal Z distribution. Okay, and we're going to have two critical values. All right, and remember the tails are alpha over 2. Just like a confidence interval. Not really important what that is. What we do need are those critical values. So let's go ahead. Again, it's 0.01 two-tail Z distribution. So this is table A2. Okay, so again, our alpha is 0.01, and we'll just remember again, this one's two-tailed. So our critical value is a Z critical value, and Z critical values are always in the bottom row here. So we go all the way down to here, 2.576 for the critical value. Okay. So the critical values are going to be negative 2.576 and positive 2.576. So if our test statistic goes outside of that range, then we'll call it statistically significant. And our test statistic is outside of the range. It's in the left tail. So ZTS is negative 2.85, which is landing over here in my left tail. And when it goes in the tail, we consider it significant, either tail on a two-tail test. So I'll go ahead and make that note. Okay. And let's go ahead and put in what we've got here. So the critical values are negative 2.576 and positive 2.576. And yes, the statistic indicates the sample proportion is significantly different from the second sample proportion. Okay, good. So check that. And we're good to go. Next thing is we're going to want a p-value. So when we go to table A1, yeah, I'm going to try and squeeze this in. So pardon me for one moment. So those are my z critical value. I could have put that on there. So let me just zoom in and identify. This was my negative z critical value, positive z critical value. Got that. And then next to it, I'm going to do p-value. So same bell curve here, but this time I'm going to put my z test statistic a little deeper into the tail here. So that's the negative 2.85, which is my z test statistic. I need the area of the tail there, so I want this left tail. You may remember that it's on a two-tail test, you have to do both tails. Okay, so I'll also shade the right tail. This starts at positive 2.85. Okay, but we just need to do one, and then we'll double this. So let me zoom out a little on that. We're going to look at table A1 for this, and as it says, use table A1 to get our p-value. Okay, so I'll just slide up to table A1 here. Okay, there we go. And I think the z statistic was negative 2.85. Let me double check that again. Yeah. So up here, we'll go negative 2.8 and 0.05, like that. So you see the area of that tail is tiny. It's 0.0022, which is less than 1%. We'll double it though for the p-value, 0.0022. So let me slide back. Okay, so just in that left tail, it's 0.0022, and by symmetry, the right tail is also 0.0022. So the p-value is twice that, 2 times 0.0022 here. So I think I can double that in my head, 0.0044 for the p-value. Okay, and let's pinch out and we'll go back here. Okay, so let's put in the p-value here, 0.0044, and fingers crossed. Let's see, where is it? Yeah, this is good. And now we want to dial in our test statistic. So just on the picture here, so the test statistic is negative. Don't end up on the right when it's a negative statistic here. It's negative 2.85. So I'll slide way back there and watch my statistic go down to negative 2.85 right there. Teeny little tail. The area of the two tails combined is 0.0044, which is exactly what we got. So that's good. And again, whenever the p-value is less than alpha, we'll reject the null hypothesis. So just the last statement here, the p-val is 0.0044. I'll go ahead and put 0.00. That's basically just going to round up a little bit above 0%, but we're comparing the 0.00. I'll go ahead and put a 44 there in a light color so that we remember only to focus on the first two digits, and 0.00 is definitely less than 0.01, which was our alpha. Less means we reject the null hypothesis and support H1. And as a reminder, H1 had said that P1 is not P2. Let me move that a little over so you can see it better. Okay. And so let's go ahead and answer it. Because the p-value is less than alpha, we reject the null hypothesis and support H1. Should be good to go. And looks like we got everything correct. So we're good to go on that one. Okay, everybody. So next I wanted to take a look at question number 5. So I think we'll go ahead and jump right up to that. And so this one is similar to the last one that we did, which was question 3, but this one doesn't explain the process now. So by this point, you should kind of have a sense of how to do the problem. So I'll go ahead and just jump right in here. It says most teens who experience clinical depression never receive treatment, even though depression has many, that should say, effective treatment options. In a clinical trial, 2 groups of depressed teens were created by random assignment. The first group included 79 teens who were given an antidepressant, fluoxetine, with psychiatric therapy. Of these, 57 improved meaningfully, whatever that means. In a similar group, 113 teens, placebos were given with blinding, also with psychiatric therapy. Among this group, 65 improved meaningfully. Let's test the claim at a 2% significance level that the proportion of teens who improve after the fluoxetine treatment is greater than the proportion for patients who received a placebo. Okay, so let's see if we can identify all these problems. So in the first sample that was mentioned, that's the fluoxetine group. There were 79 teens, and of those, 57 improved meaningfully. Those are the successes. In the second sample of 113 teens, those guys just got counseling and a placebo, and 65 improved meaningfully. So that's a lot, but there were a lot more people in that group, so it's not that surprising that more improved than in the other sample. The real question is, what's the proportion? Okay, I am just going to leave that for the moment. Let's set up these claims. So it says that the proportion of teens who improve meaningfully, I guess, after the fluoxetine treatment is greater than the proportion for the patients on the placebo. So the fluoxetine group was the first sample, so the proportion there, P1, should be greater than the proportion in the placebo group, P2. Okay, so that's our null hypothesis. Sorry, that's the alternative hypothesis. The null hypothesis would just, of course, say P1 is equal to P2, like that. And then we'll go ahead and put those in here. So P1 equals P2, and for the alternative, P1 greater than P2, like that. And right, left, or two-tailed. Well, pointing to the right makes this a right-tailed test. Okay, so we'll go ahead and pick that. And we should be good to go there. Now, successes and failures. The criteria are at least 10 successes and 10 failures. So we have the successes. In each sample, there were more than 10. So 57 in the first sample, 65 in the second sample. That's a check on both of those, but we got to count the fails. So in the first sample, the fails were 79 altogether, minus 57 successes. What's that? So to 22, which is greater than or equal to 10. I'll do that random. So greater than or equal to 10, and check. Okay, so with the other group, we have 113 in the sample. Okay, so minus the 65 successes. I don't want to do this in my head. 113 minus 65. So I get 48. And of course, that's the right size. So we'll just say 48, which is greater than or equal to 10. So check mark there. So yeah, so for the first sample successes we had 57, and failures we had 22. Second sample 65 successes and 48 fails. Yes, the criteria are satisfied in every case. I'll go ahead and check all that, make sure I didn't screw anything up. Yeah, we're good. And then for the sample proportions, let's go with that. So with p hat 1, here I'm doing x1 over n1. So x1 is 57, and n1 is 79. And again, 3 significant figures here. 57 divided by 79 is, we'll go with a 0.722. Okay, and then the P2 hat, we do x2 over n2. So the x2 was 65 over 113. So let's check that. Okay, so that's 0.575. Okay, so we'll need that, and then we'll also need the pooled proportion. So I guess I can put some of these numbers in, pardon me, for just one sec. So p hat 1, 0.722, and that's the decimal. Okay, p hat 2, 0.575. Okay, I'll check that. Good, and then the p bar. All right, so p bar x1 plus x2, this will be 57 plus 65 successes out of the combined sample sizes, so there'll be 79 plus 113. Okay, so let's do that. Again, a little more complicated fractions here, so I'll use the fraction button. And 57 plus 65 on top. And on bottom, 79 plus 113. Put a decimal after one of these numbers to get a decimal answer. And here we'll go 0.635. That should be right in between the two proportions. Again, 0.635. And it's sort of worth noting, that's sort of the average number of teens that improved meaningfully. But in the fluoxetine group, it was 72% of the kids improved. And the non-fluoxetine, only 57.5% improved. So it seems like there's a bit of a bump, and you've got a better chance of improving if you're taking the fluoxetine and getting the counseling. So a lot of these medications work. None of them are perfect, but they really make a difference for some people. Anyway, so we're doing the P bar and the Q bar. My P bar is 0.635. I'll go ahead and put that in. Should be okay. And then for my Q bar, we have to do 1 minus P bar. So I'm going to squeeze it in down here. Okay, so on the calculator, 1 minus 0.635, so 0.365. Seems like a transposition error. but it's not 0.365. Oh, what am I doing? Okay, I mean to be putting it over here. 0.365. Okay, should be okay. Fingers crossed. Yeah, it's all good. Next is this horrible test statistic. I just happen to have the formula already written down, which is nice for me. And so now I'll start putting in some of these numbers. So the p hat 1, to see how different they are. So p hat 1, which was 0.722, minus p hat 2, which is 0.575, minus the mean difference, which is hypothetically 0. And in the denominator, p bar or q bar. So the p bar is 0.635 times q bar, which is 0.365. And then over n1, which was 79. Okay, and then plus, same numerator, 0.635 times 0.365. Okay, all under that square root. And then that sample size is 113, so it's divided by 113. Like that. And then this statistic will be different from the last one, so make sure to erase that. And so here we go with the calculator. Let me wipe the screen. Okay, start with a fraction. 0.722 minus 0.575. And you could say minus 0 if it makes you feel good, but it doesn't do a thing. Over square root, then a fraction, and in the numerator, 0.635 times 0.365. Okay, over n1, that's 79. And then arrow to the right, but don't leave the square root. Okay, plus another fraction, still under the square root. Point, same numerator, 635 times 0.365, like that, over 113. So we get 2.08, and it asks for 2 places on this. So just go ahead and put it down here. 2.08. I have high hopes as I key in 2.08 up here. Just gonna check it. Good to go. Level of significance, our alpha, I don't think I wrote it down anywhere, but if you go back up to the top, it says 2% significant, significance right there. So my alpha here should be a 0.02, so I'll add that to the work here, 0.02. All right, we can put that down below here. Like that. And then our critical value. So remember, this one's a right-tailed test. And all critical values come from table A2. And it wants the Z critical value. Those are in the bottom rows because this is a Z test here. Bottom row of table A2, our alpha is 0.02 and it's a one-tail test. So let's pop over to that. Okay, 0.02 one-tail, that's this third column, bottom row. So hopefully you're with me and you're seeing a 2.054. That's our Z critical value. Let's slide back to the problem here. So 2.054 is our Z critical value. make a little space there. The test statistic is a little bigger than that. So I'm just going to kind of put a little dot to the right. So that's our Z test statistic, 2.08. Pardon me for moving this down. Okay, so that's going to be considered significant because it's in the tail. Okay, and then I'll go ahead and, doesn't matter, but I'll shade the tail because that's what I always do. Why would I stop now? Okay, and then I need that p-value. So this one's a right-tailed test. We will not be doubling the area of the tail, but we do need to look up our 2.08 Z test statistic. Okay, I have to move things down again. Okay, so let's look up 2.08 on, again, it says on table A1 here. Just to again remind you sort of the logic. I didn't answer this one. Hang on, let's put in the critical value. It was 2.054. Okay, and yes, the statistic was significant, being just a little bit bigger than that. And so now our p-value. So we're just looking at 2.08 here on table A1. Just as a reminder, this is a Z distribution problem. We're doing a p-value. P stands for probability, and we need a probability table for the Z or normal distribution. So if you go up, you look at this one here, this table A3 is a T distribution. That's no good, but it is a probability table. These are all probabilities. Okay, that's not what we want. These are critical values. That's not what I want. Okay, these are cumulative probabilities, it says, for the standard normal, and it even references the Z here. So this is the one we need. Positive 2.08. 2.0.08, like that. So this is 0.9812. I would normally say, hey, is that the p-value? And then you guys would say, no, that's not the p-value because this is the area to the left, and we're doing a right tail test. So the area to the left is 0.9812. Let's put that in here. So I'm just going to put it down here, 0.9812. But we want the area to the right for our p-val because it's a right-tailed test. Okay, so let me clear on this, and we'll do the complement. 1 minus 0.9812. Okay, and so you get 0.0188. That would have to be the p-value. Okay. And so again, I did the complement. Maybe I should have put that down. So it's right tail p-value. Anytime you're doing a right tail, you want to do 1 minus the left tail, 0.9812. So that's the 0.0188. Okay. And so that's our p-value. I'll go ahead and put it in over here. Like that. Hopefully. Yeah, it's good. Now I'm going to dial in my test statistic, just sort of draw the picture. And you see the test statistic just barely go past the critical value right there, 2.08 for my test statistic. This is a bug. Uh-oh. Okay, so somebody, oh boy, let me see what it's negative everywhere, God. Okay, so I'll have to fix that. It's close. Anyway, the p-value the z statistics 2.08 here, and which is great, and the p-value is 0.0188, which is correct. But this is 0.0187, and it's got a minus sign, and that's a bug in my program, so I'll go back and debug that soon. Anyway, the p-value, again, 0.0188. I'll obscure the 88. Okay, and remind you that the alpha was 0.02, so 0.01, yes, is less than 0.02, which is our alpha. Less means reject HO. And support H1. And H1 had said that the proportion of the kids on fluoxetine was higher. That the kids on fluoxetine that were getting meaningfully better from their depression is noticeably higher. So that is, the P1 proportion for fluoxetine is bigger than the P2 proportion for the kids that aren't on the fluoxetine. Okay. So then I need to kind of just see this in words. I'm looking for the data supporting the claim that the proportion of kids meaningfully improving from their depression under fluoxetine is higher than the proportion of kids who improved on just a placebo. So the data do not support, now the data do support the claim here, that a larger, let's see if I can get it here, that a larger proportion of depressed teens on fluoxetine with therapy will improve meaningfully when compared to those given a placebo with therapy. So that seems good. Oh, I forgot to say I'm rejecting my null hypothesis above. I think everything should be okay, but I'll go down and double check everything. Yeah, everything's perfect. So just go ahead with our 11 out of 11. And best of luck to you all.